Thank you very much for inviting me to speak here. I will speak about this joint work with Joseph and Veronika, my wife. And since this is all recorded, I should better mention that this work was supported by European Commission, Foundation for Polish Science, and my co-authors were supported by Polish Ministry and NSF. And I would start with defining the four notions that I have over there, and then I will explain the notions that I'm using in the definitions. So first of all, I will work with a projective variety in some projective space. And if you want, you can think that X is really a Veronese variety. The variety of some other vector space inside projectivization of the symmetric tensor power of this, and this is just the set of simple tensors, simple symmetric tensors. Or you can think of Segre variety, with 3 factors if you want, or you can take more factors. By the projectivization of A tensor B. C. And this is also the set of simple tensors here. The objects which were showing up here a bunch of times already. And I would like to define the rank, the border rank. These are the notions that you probably already have seen, and then the other ranks as well. So the rank, X rank of a point. Point is always in the projective space PW. It's just the minimal R that P is in the linear span of some subset R, where R is a finite subset of projective space. Length. So in case of the Veronese variety, we just get Waring rank that Enrico told us about yesterday, and other people as well. And in the case of Segre variety, we get the tensor rank and the other usual notions in the other cases, if you are familiar with them. And then the border rank.
R subset X.
And the border rank, X border rank of P is equal to the minimum R. P is, well, in the limit of RT, where RT is a family of, well, at least continuous family of subsets of X. again of length, each of length r. Right, so this was the easy part. This was the easy part. Now I should explain the more difficult stuff, and that's it will take me some time. So let me just write the definition first, and then I will explain the notions appearing in the definitions. So the Cactus rank, I listed it in a different order, so let me leave some space. So Cactus rank is the minimum. Again, the same pattern as above, except that I'm changing a little bit my object. So this is the minimum R, such that P is in the linear span of R. Now my R in X is a finite subscheme X of length R. And the middle notion, X smoothable rank of P, is the minimum R, such that it is in the linear span of R. And R in X is a finite smoothable subscheme of length R. Right. So, okay, give me a little bit of time before I start explaining this. I will just let you imagine why these notions are important and why they are, why we are interested in studying them at all. So, first of all, there is a bunch of inequalities between these notions. We have the rank is always the largest integer, and then we might have this integer to be less than, more than smoothable rank of P, which is always this, which is always more than the border rank of P, and then this one is more than Cactus rank of P. Okay. So why do we have this? Well, first of all, each finite set of points really is a smoothable scheme, and it has length R. Well, it's actually a smooth scheme, so it doesn't need smoothing. That's something I will try to explain. And so therefore, this minimum is certainly less than this minimum because we allow more objects here. Next, to compare with the Cactus rank, we just here the difference between these two notions is just this smoothability, and that's just going from here to here. I just forget one condition. So again, this is a bigger set, which is why this rank is less. Next, the border rank. Well, this smoothability is exactly chosen in such a way to squeeze between rank and the border rank, and this exactly means that our R is a limit in some sense of distinct points, which is why it lives here. But unfortunately, all the other inequalities which you could write between these numbers might be false for some conditions. Well, some people suggest to add one more, this border Cactus rank. So I will not talk about this rank. I don't know if it has any significant applications so far, so I will skip this. Okay, and why we are interested in these two new objects? Well, for applications, these guys are the main ones that we can understand and we can use, whereas these two are those that we usually see, although mainly this one. It's rather difficult to produce conditions on the border rank which are not satisfied by the Cactus rank as well. And that's why we want to understand the difference between these two notions. Okay, and in my talk at the end I would try to present you examples where border rank is less than Cactus rank. And then in Alessandra's talk you will see examples where the border rank is more than Cactus rank.
I mean, one of these should be strict, right, to make it...
Yes, thank you. In my example, actually, this will be equal to Smoothable rank, which also shows the failure of this to be an equality. Okay. So I should explain the notion of finite scheme. So in general, schemes in algebraic geometry, you may think they are difficult for some reason, but finite schemes are really easy. So we already have seen an example of a finite scheme. If it's the disjoint union of points in projective space or in X. Then this is a finite scheme of length, an example of finite scheme of length R. And if, on the other hand, we can look at this finite set as functions from R to complex numbers. Today I'm working on very complex numbers to make some statements easier. It's not entirely necessary, but it helps a little bit. I can look at functions from R to C. Well, and that's just an algebra, but it's very simple algebra. It's just C plus C R times the idea behind schemes is to allow geometric objects which have more complicated algebras of functions. So let me stick to examples first, and then I will try to formalize this. So for example, if you want to know about if we have a function from X or an open subset of X to the complex numbers, and we have this subscheme here or subset here. If we want to know the values of this function at points P1 and say f prime of P2, so the first derivative of f at P2, and for this we need to know, well, at least dimension of x plus 2 values of some expansions of f.
So by f prime of P2, you mean the full differential, or do you mean
Yes.
specific directional derivative?
Sorry, this is, in this example I just want df. So this has, for this thing we need dimension. I'm assuming x is smooth, but it's not really necessary. But just for simplicity of presentation, we need dimension of x values for this thing. And then 1 for this guy and 1 for this guy. So altogether, this scheme is going to be what, in this case, R will be just a single point, P1, and a double point supported So, what does it mean? Well, this means that for the algebra of functions, as here, I should take C for value at P1, and then a more complicated algebra here, which is actually isomorphic to C of the polynomial algebra in dimension of x variables, divided by the ideal generated by xi, xj. So I'm not interested in higher derivatives, that's why I'm killing square expressions. I'm only interested in linear derivatives, which is why I'm preserving the first grading of this polynomial. And this, as you can see, is a finite algebra, which is isomorphic to, as a vector space, is just n plus 1. It has information about the value of a function at the point and about all its derivatives. And similarly, you can ask for higher derivatives of f and higher or just directional derivatives, and there are many examples that you can see in this way. So formally,
the double point here has multiplicity and
yes, it's the really double points, so like the
multiplicity
yeah, I don't want multiplicity 2. I want the double point supported at P2, so double in x2. I don't want.
You're saying P1 is not equal to P2? Is that the question?
So the terminology double point here means
Yeah, there are, yeah, the fat point, yes. No, yeah. So point defined by square of the maximal ideal. If you prefer. That's why it's double. Okay, so formally, the scheme, finite scheme, I should say, is the geometric interpretation for finite algebras. finite algebra. OR. And now, if we can write this OR as a direct sum of OR1 plus OR2. Okay. Then each of those factors will correspond to a different point of support of the scheme. So the scheme will be supported at this K point. And has length which is the sum of dimensions, complex dimensions of OR I, which is just the complex dimension of OR. Okay, and
This presentation you need.
this one after reordering, yes, and I don't know this one.
The equivalence of categories of reference.
Okay. So now why these guys are useful to us? So the point is that we can look. So this is just the definition of an abstract scheme, so it doesn't have to live anywhere. But we really we are really interested in subschemes. So we say that R is a subscheme of X if we can if we should be able to relate these algebras to the structure of X, and we can look at functions. Well, they should better have some structure. Functions on X, perhaps defined locally in some neighborhood, in some open subset, and we should be able to restrict those functions R, and well, the functions should have always have some multiplicative structure, so we can take two functions and multiply them, and after the restriction you can multiply them in this algebra, and you want these two multiplications to agree. So the restriction of the multiplication must be equal to multiplication of the restriction. Let me just give another example. If we can look at X inside, for simplicity, affine 2 space, or which sits inside the projective 2 space. And this is just a parabola, so X equal y square. And inside here, we can look at a subscheme of length 3. And we want it to be supported at 0, 0. And isomorphic to the scheme determined by algebra E of t divided by t cubed. Okay, and this should determine the scheme. So if we think of it as a subscheme of this parabola, it will give us the information about third order functions up to order 2 of the functions on the parabola. So parabola is isomorphic to a line, the affine line. And it's just, if I have a function on the affine line and I restrict it to this scheme R, then f restricted to R is giving us the information about the value of f at 0, about the first derivative at 0, and about the second derivative at 0, while but it's also embedded in the affine 2 space, and if we have the function g from the affine 2 space to complex numbers, then it should give us information about, well, also the value at 0, but now only about one derivative.
G at 0.
Zeros, thank you. Now I should be careful which one. So this is by the y, I guess. Just double check this. And now, well, you see this is not anymore straight line. This is a parabola. So the other way around, I guess. So I have the information about this derivative, but the other derivative is already twisted. It doesn't fit into this curve. So it's not really a derivative in the direction of y anymore, but some linear combination of the derivatives in the second direction as well. And it's possible to calculate this. And unfortunately, I forgot to take my notes. And, I don't remember exactly the linear combination. Right, so all right, so our life would be much easier if
You know, replace x by t squared. It's like replacing x by t squared.
yes. So this O of R is also isomorphic to C of x and y divided by, well, the equation of parabola, and I should also have the equations that me guarantee that the cube is in the ideal, which is x, y square. Suppose some of them only are x, y. Some of them are probably not necessary.
XY solids needed.
Yeah, but if you homogenize, then you already also need the other ones. Okay. So there is one way of obtaining schemes that's relevant to our definitions, which is by limits. So if we have, so as I said, the starting example was just union of finite points, and then we moved our finite number of points, and some of them will collide. So there is a family, and all of a sudden some of them collide. And what we get in the limit, we want it to be in some sense continuous, so we should better count the limiting, the collision point with multiplicity. There are 2 points. Then the limit point will have multiplicity 2. And if there are more points, obviously this is going to be more. And then if but there is also an extra structure, not only just number, that's multiplicity, but we can say, for example, if in which direction they have, from which direction they have collided. So, for example, if one point was fixed and the other was coming from some direction, then we at the end result we just get the direction of the incoming point. In general, it's kind of an algebraic process to determine exactly the structure of the limit, but it's always possible to do. And there is a notion of, it's called flat limit. So if we have a family, now I should better assume that this is algebraic, or at least holomorphic. Family. So some base T, which is flat, and let me not explain what flat means. It's just essentially for finite schemes, it means that all the fibers have the same length. This is family of subschemes, of schemes. Plus properness, which is kind of compactness condition. So I don't want to consider a family like this is not a nice family, although it's a, you can define it algebraically, right? Because this part is just x times y equal 1. This is some other point, whatever it is, and then this I would consider the projection onto the base. It's proper, it takes care of this kind of stupid examples. And then if I have a flat family such that for an open subset here, the image of this open subset consists only of smooth schemes, so just disjoint points. Then,
what's the condition on U?
sorry?
What is the condition on the subset U?
It's open subset, or well, actually any non-empty subset. Any non-empty subset will be good enough because to be a disjoint point is an open condition. To be a union of disjoint points is an open condition, so you don't need to worry about this topology. Then the limiting point, so anything scheme for any outside you, we say that the fiber RT is smoothable. And that's the definition of the set of smoothable schemes. So in brief words, they are just limits of disjoint union of points.
I'm not sure what the logic of this definition. I mean, what?
Right. Sorry for that. So this should be the formal language to have an honest definition. And the formal language is as follows. So if we have a flat family of schemes, which is an algebraic family, finite schemes, then...
So this is the definition of smoothable.
Yes, this is the definition.
What wasn't clear, so it should be like definition, a scheme is smoothable if it has this property.
If there exists such family. Right. And then there is I should be able to. I should explain also the linear span of a scheme. If I have a scheme R, I should say what is its linear span, and this is going to be just, well, as usual, linear span. This is the smallest linear subspace that contains this scheme. Now, what does it mean that a linear subspace contains this scheme? Let me not give a formal definition. Instead, I just draw an example. So if I have a scheme which has information about the first derivative in this direction, so it's not contained in just zero-dimensional scheme, in just zero-dimensional linear space supported at this point, but it's contained in this line. Similarly, if I had this example here, which had information about the first derivative here, in this direction, and then a little bit twisted second derivative, then I can't have it contained in a single line. I really need a plane for that. So the linear span of this scheme is the plane that contains the parabola.
Yeah. So for smoothable ones, it's okay for me to just think of the limit of the span of the R points, or is that?
No. No, that's the point. So that's if I have a family.
So is the dimension of the span of the scheme always equal to its length, or can it be less?
It can be less. So let me just give your favorite example. This is a finite scheme. If there are 3 points on a line, then their span is a line. Similarly, if you have a scheme, if you have a non-reduced, that's a more complicated scheme, it still can have length 3 and be contained in a single line. So it's true, though, that if I have a family parameterized by T, and if I take the limit of the linear spans, on the other side I take the limit of RT and the linear span of this, then there is an inclusion going this way, but not the other way, not necessarily the other way. And we would be very happy if this was always equality. That's if equality always holds, then smoothable rank is equal to the cactus, sorry, to the border rank. Okay, so let me just give you some classifications. We have, if we have any smooth variety X in a projective space, then we can look at the secant varieties of X, which is just a set of points in the projective space, such that, well, you can define it in various ways, that the rank of P is at most R, and then you take the closure, for example, or you can just say this is the set of points where the border rank is at most 2, or you can replace the rank by smoothable rank. All these definitions will give you the same thing. So let me just, and then you still need to take the closure, or if you don't want the closure, you just have to use the border rank. Okay. So if R is equal to 2, if R is equal to 1, then this is just 1 over X. If R is equal to 2, and we have a point in the secant variety, then P is either so the case 0 is that P is in X, the case 1 is P is in the linear span of X and Y for some X and Y in X, and then the third case, P is in the linear span of a point with single tangent direction, which just means that X is that P is in the tangent space to X at some point. And this is a classical theorem. So in this case, we always have smoothable rank. So if the border rank is equal to 2, then the smoothable rank is equal to the cactus rank of P, and is equal to 2. Or we can take less threshold. Here is, for this statement is a bit important that X is a smooth variety. And also the other implications hold true. Okay, but already for R equals 3, in the interesting cases, we have failure of this inequality. Of this equality, sorry. R is equal to 3, and P is the point in the third secant of X. And I will need to assume a little bit about X, but you can think it's, well, remember the examples that we started from. Or this is the Veronese. then well, we can have P in the second secant variety, which we just referred to the previous case. And the other cases, well, there is a P in a linear span of x, y, z. X. Or there is point that's in the linear span of a scheme like that. So there is y and the tangent direction. Or we can have a point in the linear span of a triple scheme, degree 3 scheme or length 3 scheme, like the one in the example before. So this is point x. Next, then a tangent direction. And then second order derivative. And there is a fourth case which doesn't show up in the Veronese case, but it does show up in the Segre case. That P is in the linear span of two tangent points, two schemes like this. So remember, R was 3, so we are in the third secant variety, but we are here taking two disjoint schemes of length 2. Altogether, they have length 4, and but we require that x and y are contained in a line that's contained in x. That's why it doesn't show up in the Veronese variety, because there are no lines contained in the Veronese variety. And that's all for these cases and several more cases. These are all the possible forms of the points in the third secant variety, and well, all these have smoothable rank equal to the Cactus rank equal to the border rank, whereas this thing has smoothable rank equal to 4. And the Cactus rank is also equal to 4, but the border rank is equal to 3. Well, at least for sufficiently general point like this, this holds. It can be less, but there are examples where this is equal. And then for Veronese variety, we also have similar examples, but we need to go to the fifth secant variety for that. So if R is less than 4, then and x is the Veronese, then we always have just the border rank here, and we always have smoothable rank equal to the border rank, equal to the Cactus rank, and if R is equal 4, if R is equal 5, then we can. Then there is an example, which is x zeros the cubic, 0 squared y0 plus x 0 plus x1 squared y1 x1 plus x1 x1 squared y2. This lives in S3 C5, and the smoothable rank of X class of X is equal to 6, whereas the border rank is equal to 5. And well, you can write, well, to prove to see that this is this has border rank 5, you just write explicitly this polynomial as a limit of 5 cubes, the sum of 5 cubes, whereas it's a bit more complicated to see this is not, that this holds. Well, it's easy to see that it's at most 6, it's not so easy to see that it's exactly, there is some calculation to perform.
Excuse me, Jarek, you can prove that also the rank is 6 in this case.
The rank here, the rank of this guy is
He has the inequality with the rank of the smoothable.
actually equal to 9, which by chance this is more than 8, which is generic.
So if you go to higher degree, you have to go to higher order rank to get these kind of examples.
Exactly. So if well, the minimum you need is that if you're looking at points in the SDV, then to obtain, well, let me just put it as a positive statement, if the border rank of C is at most P plus 1, then the border rank is equal to the smoothable. I should also say that this was a talk about the difference between smoothable and border rank, but there are non-smoothable schemes, and they produce difference between Cactus rank and smoothable rank, which is even more delicate than this issue. Okay, thank you. I'm sorry for going over.
Questions?
So could you give an idea of how you prove the smoothable rank is greater than the border rank in that example?
In this example? Well, so this I've said that I didn't write it, so this is true for sufficiently general point of this type, and well, it's not entirely trivial, but we prove it in our paper that the points of this type are not, the general point of this type is not of one of the types above. Well, I mean, this is a...
Yeah, but so let me ask the question a different way. Smoothable is not algebraically closed condition. So
right, that's why we have to take generic one.
So it becomes very delicate.
Yes, well, let me just do it again. So there is we can use the classification of schemes of length 3, at most 3.
Yes.
So these are, well, this is one example. So 3 distinct points. There's one point and the double point, or
It's not on the list.
it's not on the list. Yes.
That's not a good proof. Well, it's a good proof in the sense that it proves the theorem, but we're going to run out of lists very soon, right?
Right, and then there is algebra that comes to our help.
Right. So what kind of algebra do you use when you
That's
don't have a list?
okay. So
It's non-algebraic property.
which is not
It's algebraic.
it is an
Well,
algebra.
it's not non-closed property. Sorry.
Right, that's why we use algebra, not geometry. So Well, I mean, I didn't say that, but there is an algebraic definition of the linear span. It's just that if you have a subscheme of a projective space, then there is you can define the ideal of the functions that vanish on R, and it's an ideal in the symmetric algebra of W dual. And you just look at the linear span of R. It's just the zero set of the ideal.
Oh, it's pretty awesome. Oh, I see. So it's
And then you just look for co-length. So the length of scheme or is just equal to the dimension, complex dimension of, well, maybe that's degree of the quotient algebra, symmetric.
Yeah, sort of the measure that degrees
I see then. So now I'm starting to understand. So this kind of modification of what Zach and I did in this more general setting.
Yes, you can see this. For sure, you can think of this as a generalization. And if you have, well, you just look for, so if you have length 3 in this case, you just look for algebras which have this length, this condition, which is very restrictive already, and then you look at this degree 1 functions that can show up in this ideal.
So then I was wrong. It's not. You're not looking at qualitative properties about how it's situated. You're looking at something else.
Yeah, I'm looking at this too, but I mean, it's in the case of the Veronese, it's a little bit simpler because you can look at the ideal of R inside the projective space V.
Other questions? Maybe I'm just treating that. Of course, you can repeat the definition for, I mean, smoothable is a local definition, okay? So you can ask for any other kind of local properties, and this is good for writing a lot of papers, or if you are old enough, it's good for giving thesis. But let me ask if you ever saw any problem like that going the other direction. So asking that your decomposition has some global property. So for instance, one thing would be to ask for, say that this set of points is arithmetically constant, to say 1. In that case, you have probability that you get some, say, vector bundle, and so you are asked, in this case, you have this Pfaffian stuff, and you are asking that the linear space is defined by Pfaffians in terms of the local coordinates of the decomposition, or things like that. Have you ever been some kind of...
What Pfaffian stuff? I don't understand.
I mean, if you ask something on the global geometry of the decomposition, this means something on the equations of, for instance, let's say that your x is a surface. Then asking that your decomposition is arithmetically constant, this means that you have an arithmetically Kolmogorov ranked bundle and on the surface. And this means that every hypersurface containing your set of points is defined in terms of Pfaffians of the coordinates of your points. So it may be as some application to know that your point sits in a space that can be defined by Pfaffian. This is just a rough idea. I have no reasonable way to do that, but just asking if you ever saw something in the other direction. So asking global property of the decomposition instead of local properties.
No, I haven't. I guess it's difficult to track the global properties of this.
Yeah, okay, that's everything is difficult here.
Yeah, well, and then the motivation I mean, this kind of problems are in some sense motivated by applications, whereas I don't see direct.
Well, you embed
applications.
your decomposition in higher, I mean, in some sort of, not just saying that this is, you are something more algebraic, so you are trying to get a description of your object in terms of something which is more algebraic, but I don't know if it's a sort of application. So I told you that was cheating.
Let's thank Garrick again.